Okay. Hi. For those that are online, can you hear me okay and see okay? Okay. That one's an easy one. All right, how are you guys doing today? Good. Carly, do you mind if I put you on the spot?
Yeah, no, I can go for it.
Okay.
Just, yeah. Okay.
If you want to just come right behind us.
Yes,
So.
I can do that. Okay. There we go. Hi guys, I'm Carly Higley. I am taking this class. I also work for the Department of Electrical Engineering as a tutor with John Bulkey. So I've taken Circuits 1, I'm in this class, and then I've taken Circuits 3. So basically what that means is we hold open office hours, which you can see the full schedule. It's not just me, there's like 5 of us now. You can see the full schedule on the just electrical engineering Canvas page. Oh, do you have it pulled up?
No,
I'll
get it.
Anyway,
Yeah.
you can find it online. So I do Zoom appointments. I know that Ken also does Zoom appointments, so you can do that. Or you can just drop in for those office hours if you have any questions, if you need help. Yeah. Do you want anything else from me?
That is great.
Yeah.
So do contact Carly or some of the other tutors. Be aware. So this is the new schedule that's on here, and you can see Carly is listed on there.
So those, sorry, it's kind of weird. So the red ones are times in just that people will be in that area, and then the green ones are times that they are like in the class. So like I'm in this class every time we have class. And then the ones along the bottom are Zoom meetings, just in the evenings.
So the Zoom ones you'll want to schedule. The other ones you can just drop in. The student lounge is in the hallway between the main office and the advising suite, right around the corner from your labs. So MEB 2255, and there's just some tables out there, and there'll be a sign on the table that says, I'm a tutor, basically. So you can go and sit down there at any time during these open walk-in times. They are available to ask for homework help or any other questions if you want to set up a time. Study as a group. Carly's up for that too, I'm sure.
For sure.
So please reach out. Know that support is available. Thank you, Carly. All right. So exam Wednesday. Make sure to go to the Engman lab. It's upstairs in 210 L210 upstairs. And if you're going to take it on your own computer, make sure that you bring your computer that you're going to take it on. And then anybody who is remote or online, you need to make sure to reach out to me that you're going to be taking it at the same time. And I will send you a link. Otherwise, you do need to come in person during that time. Let's see. Email or Canvas message. What do you mean, Daniel? Oh, email or Canvas message me. Canvas is preferred first if you're going to reach out to me to take the exam remotely. Try Canvas first, and if you don't get a link before Wednesday, do reach out to me through the other email. All right, any questions about the exam location? Open notes, open book, online calculators, no online simulators, so just no simulations, but you can do scripting if you already have scripts written, MATLAB, other scripts. Just make sure to include those in your submissions, just so if you do make an error.
If we write the scripts, say for like a graphing calculator, do we need to just make sure to copy those as well, or?
If you can, just in case you make an error.
All right.
It's nice to be like, I got partial credit, but I did have an error somewhere here, and so that way you can tell.
I was just asking because I'm not so sure. I don't know how easy it would be to copy. So.
Yeah, if you can just take even a screen picture.
Okay.
As much as you can include, that will just give you more opportunity if there was an error that you'll get the partial points for it.
Okay.
If you don't include it, that's fine too. If you end up with an end result, it may be that I might ask, like physically ask and do a verification step if you had the right answer with no justification kind of a thing. And so those that are online, do note that there is an extra verification step that will be taken. I will reach out to you after the exam to do that verification step, if you do take it only online during the exam. Okay, yes.
So can we take it like on the computer upstairs, but then have our laptop for the script and stuff?
Yep. Yeah. So if you, depending on how you want to submit it, if you're just going to take screenshots with pictures and submit it, that's fine to take it from whatever one you're doing. And it's nice to have both computers so you have extra windows open. So yes, you can do both, logged into the computer and your own computer there too. All right, any other questions about what you can bring, what you can have? Okay. All right, so I wanted to kind of go over a few extra problems that, like, how do you identify, again, is this series parallel or neither? Adam, what do you think?
It's series. If we could do some rearranging to say move that current source, if we think about just as long as the wires are connected the same, we could move that current source to be a voltage source, and it ends up being series, but we have a voltage source in series as well. With the current source in parallel to all of it.
So you're saying to move which element?
Just move the current source up above the inductor, I think is the easy way to visualize it.
So you're saying like this?
Yeah. And then we have the,
And then this will be shorted. Like that?
yeah, and then they're, kind of series, oh.
I don't want to say like it's. I think it falls under neither.
Okay, so you have a neither.
You could solve it using the similar technique, but you'd have to take into account that, that current source is there and how you provide stuff, so you can't use the cheat sheet for that, you have to.
You could derive it just with the differential equation.
Mhm.
So that would lead into that's neither a full series or a full parallel.
Yeah.
Okay. So hopefully you do see it is neither. Whoops. So the reasoning is for series, it has to be the same current going through the capacitor and the inductor. So that's what you kind of are really looking for. For series, same current through cap and inductor. So that's not the case here, right? Because the current going through here is going to split and be, so IL plus this current, IC, is the I current. So it's not series. Parallel, what's the condition for parallel? Yep, so nodes are same on top and bottom. And that's not the case here, right? Because this node is not the same as that node. And then the same thing here, this node is not the same as that node. So even if I moved the capacitor before or after the resistor, or even before or after the voltage, it's still going to have one of those locations not the same. So I would have one node the same, but the other side would not be the same. So therefore not in parallel. So this one ends up being neither. All right, I was gonna get, if this one will show up. one's not showing up. Grab 19. Okay, none of these are pulling up. Huh. Okay, none of those are pulling up. All right. Duplicate. Okay, what about this one? Sorry, just one second. Carson, to answer your question, he's asking if a physical piece of paper is needed or if you can just do it on your iPad. You're fine to do it just on your iPad if you want, just depending on how you work. So you don't have to have a physical piece of paper if you do it all on your iPad. Okay, so back to this one. What do you guys think?
Sort of splits it into two kinds of surface from what I see when you're open it. Like on the right side, it would be seared.
Yeah, see?
But on the left side, I'm still working that one out.
The left side would be serious, but the right side would
Okay, so I'm hearing some people saying like split this up, right? Okay, so the final circuit is what's going to determine this. So we'll look at the final. And in the final, you're going to have this open. So this would be the final circuit. So this is going to determine what you have. So I heard, what's this going to be?
That would be just a regular RC circuit.
RC, correct. And then what about this side?
That would be series.
Okay, RLC series. Okay,
Because while there is weird shenanigans of weird different current going through the resistor, the capacitor, and the inductor have the same current through it, and that's all we need to qualify as series.
correct. Yep, so the same current is flowing through the capacitor here as it is through the inductor. That is what determines it's in series. Yes, Bobby?
We got a question like that. As for the final VC, would we solve each side separately and then add them together?
So let's do that. Let's find VC2 and VC1. Okay. So depending on what you're asked will depend on what you have to solve for. But let's do both here. So find VC1 of T and VC2 of T. All right, so VC2 is the capacitor here on the right, and VC1 is this capacitor here. Yes?
So can you move the voltage source forward?
Which voltage source?
The one on the left in RLC.
The 3?
Yeah.
So you can, if it's disconnected in the final state, you can move it.
Oh, okay.
But you can't move it when the wire is there because then it's not in series in that,
Right.
at that time.
Gotcha.
Does that make sense?
Yeah.
But to determine if it's RLC, And if, as long as it's the same current in that branch, you can move those elements. So you could just solve for that if that makes it look better to have the C and the L right next to each other. All right? Yes, Kyle?
If it's determining same current for series, is it something different for parallel, or is it parallel just determining the limits?
So for parallel, you know that VC has to be equal to VL because they're in parallel to each other, so the voltage stays the same across them. And the currents through them are going to be different. And for series, the current's the same and the voltage is different across them. Does that answer your question? Okay. All right. So go ahead and work individually or in small groups and find VC1 and VC2 is what you're looking at solving for.
C1 is 1/8 farad, right?
Yes. Sorry. There you go.
this one before. I think before that. It didn't teach you. It's just you calculate your alpha, your average, and then you do ECS. And then you just do some if statements to generate your increments. That's what you want. And then if you write like one per series and one per parallel, like basically the same.
Okay.
I'm gonna run out of time. Like doing everything by hand so much.
Yes.
Yeah, so, above the younger sister is 60. And then,
Not a bad idea.
from the other side, you're going from 0 down to, I tried to.
So, what I did is I figured 2 amps. So I did 8, is 1 over 8 minus 2 amps. I just have to know that basically. Oh, yeah,
So this is gonna be. Right, that would put that point at 0. Yeah.
Okay.
6, so it
So
would be
then
right
right
here.
here would be -3.
Yep. Well, once you break it apart, like 0 plus, if it's in series with that inductor, isn't the inductor gonna force? Is that how it works? If it's connected to ground, it has a 0 current? No. Why would it have the current of going through like plus or minus 5 volts? Like there's a little loop right there, right? And so, since it's connecting the ground voltage, then the 10 ohm resistor needs to have a voltage of 5 volts. Right? Actually, that's not what I thought.
All right, so I have two problems, so we're gonna move through this pretty quick. So RC side and then the RLC series side. On the final position will be where you're going to find RTH. So you're going to find RTH for the RLC series will be 8 ohms. Why am I finding the RTH, by the way?
We're determining the level of dampening.
Correct. So I need to know the characteristics between the like alpha and omega naught. So the comparison between them to figure out that characteristic. So RTH for the RLC series side will be 8, and then RC on the other side will be 10. So I've shorted all of the voltage sources, opened up the current source, and so that gives me those. So alpha ends up being, for RLC series, is RTH over 2L. So that gives me 4,000 nepers per second. Omega naught ends up being 0.045 radians per second. Anybody get that far? I get some yes. Any others? Okay. From here, you can see hopefully it's overdamped. So then I need to go back to 0 minus to get the voltages. Did I?
You got, like, it's the right level of dampening, it's just the omega knots wrong.
Yeah.
Oh, then my values might be wrong.
I got
Yeah, that's what I got too.
89.44 radians per second.
Yeah, my calculator says that calculation should be 89.
89. Okay.
I'm curious. how
I
you
did
got-
these late last night, so
Yeah.
thank you for correcting me. Okay, so it was 89.
89.44.
89.44. Okay, I'm going to have some errors in the values then. Okay, but it's still less than alpha, so it still is overdamped. All right, at t equals 0 minus, it is going to give you the VC value for the source and then the current value for the inductor. From there, we're going to use those values to find 0 plus. This is our initial time. So for overdamped, I need IC0, VC0, and VC infinity for the RLC side. So VC1 is going to be the voltage on green, this side, minus the voltage on this side. And the minus on, or the voltage on the left, you can use node voltage, so you get minus 2 coming in, plus Vx over 8, and that's solved to give you Vx is 16 volts. So that gives us the value on the left side. And then with this shorted, that gives us 0 volts here, so this side will be -3. And so the VC1 is going to be 16 minus a -3 for 19 volts. Does that make sense? Okay, then we need the current I1. And so, or IL1, sorry. So the current IL1 is going to be, there's 0 coming in from the current source because that's floating. So my equation is IL1 plus I1 equals 0. So I guess I didn't write that one. And then, so that gives me IL1 is just equal to negative I1. And I1 has 0 up here, so 0 minus 5 over 10 will be how I find that value. And that's a -1/2, so IL1 is a +1/2. You guys all following that one? Okay. All right, then in the initial stage, I replace the voltage source and I replace the current. Oh, and then VC2 is going to just be 0 because it's in parallel with the wire. If I don't quite see that, I can notice that it's all the same through all those. Okay. All right, so then for the other initial value, I need IC1. And with this open, you can see the IC1 will be equal to 1/2. It will be equal to IL. And then VC2 will be 0. And IC0 will be a half, and then VC1 will be that 19 volts.
Can you go over why IL1 is equal to IC1 again?
So redrawing this, the switch is open, and so IC1 is in the same branch as the IL.
Oh, okay, yeah, no, I see.
You see that? Okay. Yes,
Okay,
Marley?
So the final VC1 is still 19 volts.
Uh-huh.
Wouldn't there be current, like, going the other way on that 8 ohm resistor, so it would change the voltage drop?
So the final circuit looks like this. So this side is, I grounded that side. So the current going through the 8 ohms is going to be all of the 2.
Okay, I mixed up 0 plus and final. Yeah, no, that makes sense.
Okay, so you see that is the same,
Yeah.
the same current. So that will still give me 16 volts above there.
Mm-hmm.
And then I still have the -3 on the other side. So it's still going to be 19 volts across that one. And then VC2 for the final is going to be, there's no current in the 10 ohms, so that will just be 5 volts. Do you guys see that? Okay. And then using the overdamped equation set, I need S1 and S2. So these are going to be wrong. Since my other values are wrong. So I don't know what A1 and A2 are. I will refigure these out and post the values, but all right. So from there, you're going to find S1, S2, and then plug them in for A1, A2, and then you're going to get your equation for VC of T. For the VC2, I'll go back and find that, and then I'll post these so you guys can check if you want to use it as an exercise. For VC2, it's the final plus the initial minus final, e to the minus t over tau. And so the final was 5, the initial was 0. So it's 5 plus 0 minus 5, e to the minus t over tau. And tau is RTH times C. And RTH for the C side was 10. So 10 times 1 over 8 for a value of 5 force seconds. So this will be the equation for the VC of 2.
I thought that the capacitor C2 was valued at 1 over 10 farads, not 1 over 8.
Probably, yep, sorry. Yep. Thank you.
That's a much nicer number.
Yeah, it's just 1.
I was trying to find things where, okay, 1. So that makes it easier. 1, yes, thank you. So I'll correct that error and then I'll get the values so you can have an actual value for VC1. Okay. This problem. What do you think with this one? Series, parallel. I'll tell you it's one of those.
This is the same one we just did.
No.
No,
It's no. The 5 ohm is a resistor instead of like capacitor.
yeah, and then the switch closes at t equals 0.
Oh,
So it's a
very
different
similar,
circuit.
but-
It's similar but different problem as you're going to see in a second. Quite a bit different.
So at T equals 0, the switch is open?
So t equals 0, the switch becomes closed.
Okay, so it starts open.
It starts open and then it becomes closed.
Actually, yeah. It doesn't, but it's just one switch. Right.
So what do you guys think?
It's in parallel. It's an
Okay.
LLC in parallel.
So this will be closed and it is in parallel. So it will be RLC parallel. All right, spend the next 5 minutes on this, as much as you can get done, and then I'll go through a solution on this one. All right, so for this one, find it's in parallel, and then RLC, or alpha for parallel is 1 over 2 RTHC. And so that ends up being 0.9 meters per second, and then omega naught ends up being 100 radians per second. So that becomes underdamped for this one. Did you guys get that? Okay, seeing some yeses. Okay, great. So RTH was found from removing the voltage sources, opening the current source, and then the pathway between A and B is going to be a pathway through the 10 and a pathway through the 5 and the 8. So it's going to be 10 in parallel with 13 to give you a 5.65 ohms for that RTH. From here, you're going to want to find, so for underdamped, we need IL 0, IL infinity, and VL 0. And so we're going to need the initial values. So I find T0 minus first, and then use those to find T equals 0 plus, which will be my initial time. So for 0 minus, I found the Vx value, and then if I know the current, to find IL, and so Vx I solved to be 56 over 13, and then IL is going to be Vx minus a minus 3 over 5. Yes?
For VX, I found it to be 8.
I could be wrong with this. What's 56 over 13? It's 4.3. Let's see, minus 2 plus Vx over 8 plus Vx minus a minus 3 over 5.
Ends up to be VX times 13 over 40 equals 2.6. Actually,
I mean, I did a different method, but I got the same pi value. So
You got 8 too, or no?
I did it a different method where I didn't use nodals, but I got the same pi at the end as you did.
so I
Okay.
messed up.
You
I
you saw your very.
instead of subtracting 3.
Ah, okay. I was gonna go put that into Wolfram Alpha because I'm like, I could be wrong. Okay, so 56 over 13, and then IL is Vx plus 3 over 5 for 1.46. So how did you do it, Carly?
The way that I did it was I took the current source and the resistor and I transformed them into the voltage source and resistor,
The Thevenin, like this. Okay.
and then just did the loop on the left-hand side to figure out
Okay. So that would be another way is to change it first to the Thevenin. I ended up later doing Thevenin because it was easier. So changing the Thevenin was easier for the T plus. T equals 0 plus. So Thevenin, remember, is where you can take out a little bit more complicated circuit. In this case, we can see that if we don't take that out, we have an unknown node here, and we have an unknown node here, so we would have just two sets of equations. And so if we change that into Thevenin, it just simplifies the circuit a little. So Thevenin is you just disconnect it fully, so this is all you have to solve for is the 2 amp and the 8. And then I'm going to put that back at this point, A to B. And so I can do the node voltage again on the top, which would put me at like Vx or minus 2 plus Vx over 8, and that Vx is VTH, so that gives me 16. And then RTH just opens up 2, so that becomes 8. So replacing that gives me this circuit where I replace the 1.4 for the inductor and the 5 volt. Oh, I forgot to do the 5 volts. So 5 volts over here. There's no current flow here, so VC is just 5 volts. And so VC stays 5 volts over here. So my initial VL is going to be VC, which was 5 volts. And then my initial IL is 1.46. And then for the final, again, it's easier to use that Thevenin. So the final, you're trying to find the IL here. But you need to know the current coming in. The current here, note, and then this is 0. So I have 16 minus a minus 3 over 13 plus IL plus 0 minus 5 over 10 equals 0. So IL ends up being a minus 0.62. and that's my infinity value. And then I use omega naught and alpha to get omega d. And then this becomes d1, d2. And I plug that into the equation to get the full answer. Okay, questions? Okay, RC, RL, and RLC questions on Wednesday. And open notes, open books. Everybody ready?
Ready as I'll ever be.
You're very honest. Ian's not ready. Will you be ready on Wednesday? Okay. Okay. All right, make sure to work on your group assignments or your individual assignment for the discussion, so that's due tomorrow. And get you ready for the exam on Wednesday. Yes, Xavier. These notes will be posted, yes. Yeah. So you just go to the lectures under the modules, and then I will post them on that handouts and lecture section.
You're gonna post practice quizzes or something?
No, the notes from today. And so they'll be here, I forgot to do Monday. So it'll be here under the Mondays class. All right, have a good day, study hard, and see you guys on Wednesday.
Question for our like exam assignment or whatever. So I tried contacting Cole, but like he hasn't gotten back to us for anything.
Okay.
I don't know if he's like, is he in class or is he remote mostly?
Mostly remote, I think. Let me see if he's on. Yeah, he's not on right now. All right, see you guys.
1, 2 is the one. Oh my gosh.